So for today, we're going to discuss sample problems on physical systems which are connected in series. So there could be two possible connections or interaction, and that's in the non-interacting and interacting system. So the physical systems could be any of the, I think, the 4 or the 5 that we have discussed already. So we'll have the liquid level system. So it could be one in which we have a transfer function between the input and the output, the input being the flow rate of the liquid that is changing to the tank and the head of the liquid. The other one is between the outflow and the inflow, and the other one in which the outflow is constant because it's being regulated by a pump, and then you have the inflow. Now, it could also be a mixing system. It could also be a steered tank heater, or it could be a CSTR. So any of these physical systems that you have encountered in the past, whether in this course or in reaction kinetics, could be connected in series. So far, these are the only systems that were covered in the book, now which could be connected in the two fashions that were described in chapter 7, that is non-interacting and interacting fashion. So for today, we're going to discuss some of the sample problems at the end of chapter 7 for physical systems arranged in series. I'm going to go to the copy of the book and then have it shared with you. Okay, let me share my screen. Now, I hope you can see already problem 7.4. Now, this is a combination already of the two systems that we have discussed yesterday. I say it's a combination because in the first two tanks in here, you have interacting connection. And in this third and the second tank, this third and second tank, you have non-interacting connection. So these two are interacting while the last two are non-interacting. So in this case, the pre-derived equations given by Kauhanor for non-interacting systems and interacting systems could not be used as is. Maybe we can use the interacting transfer function for these first two, but we have to derive another transfer function for this, or we could use the transfer function for a liquid level system, only that we will change the Q to Q2 and then the Q sub O to Q3. That way we can connect the two working equations together and then have the overall transfer function of this three-tank system. So let me read the problem first. So I suggest that while I'm reading this one, you take a screenshot, that way later when I show to you the solution, the prepared solution, you can still go back to that copy of yours, the screenshot of this problem. So for letter A, you are asked to find the transfer function H2 of Q, H2 divided by Q, and H3 divided by Q for the three-tank system shown in the given figure, where H2 and H3 and Q are all deviation variables. They are all deviation variables because they are written in capital letters already. Now, tank 1 and tank 2 are interacting. Tank 2 and tank 3 are non-interacting. So for letter B, for a unit step change in Q, this one, the Q that is introduced here on the first tank, so I will have it labeled here so you will see. So let's say this is the Q. So for a unit step change in Q, wherein your Laplace for that would be 1 over S, you are to determine the H3 of 0. What is the corresponding deviation of the level of tank 3 from its steady state value at time equal to 0? So this is more or less an application of the initial value theorem. And your H3 of infinity, an application of the final value theorem. And then you are asked to sketch H3 of T versus T. Okay, so in here, you will have Q1, and here you have Q2, and Here you have Q3. Okay. You have the given informations here as to the areas and as to the linear resistances. So 2, 2, and 4. So you may take a screenshot of this one. So when I share to you the complete solution of this one, you can glance over it from time to time. Now clear my markings. So what would be our solution for this one? So let me again share my screen. Okay, that PDF copy, wait, class, ha? Okay, can you see the screen already in my handwritten solution?
Yes, miss.
Okay. So these are the two tanks, the three tanks rather. And if you notice the given here in terms of the area are already written, and you have also the linear resistances here. Okay. So same as the figure that you have taken a screenshot of. So letter A, if you're going to write our required information in terms of a transfer function representation. So we're after the transfer function of this interacting system, which comprises of tank 1 and 2, and the transfer function of the overall system comprising these three tanks, okay, which has both the combination of interaction and non-interaction. The letter B, this is how you write it. So H3 of 0 and H3 of infinity, where your Q of S is the response or the Laplace rather of a unit step function, which is 1 over S. And you're required to get the or draw or sketch the response of the level of tank 3 against time. So you're going to set up your equations in here. So I have started from top to bottom really. Now, on the premise that you haven't yet known the transfer function of these first two tanks. But if you already know and you can still remember or you have memorized the transfer function for interacting tanks yesterday in our discussion, you need not go over the derivation as the one that I have shown to you in here. Okay, so but nonetheless, I placed in here the representation of the relationship between the volumetric outflows and the heads. So in here you have Q1. Let me annotate. I did not place it here because. So you'll have here in R1, just go down first. So this is your Q1. This is your Q2. This is your Q3. And this is your Q. Now, if you write the linear relationships between all these Qs, very importantly, the volumetric flow rate through the linear resistances. So you have it here in the first three equations. For Q sub 1, you have interacting systems. So you have H1 minus H2 over R1. For Q sub 2, it simply is dependent only on the level of tank 2 because this 2, tanks 2 and 3 are non-interacting already. So it's just H2 over R2 for Q sub 2. And for Q sub 3, that would be H sub 3 over R3. So these are the three equations governing the flow rates to the linear resistances and the heads. Now, if you're going to write the material balances on all three tanks, it would be like this. So for tank 1, you have this one. A1 dH1 dt is Q minus Q1. And for tank 2, you have A2 dH2 dt and you have Q sub 1 minus Q sub 2. So the flow rate to tank 2 is Q sub 1 and the flow rate through the linear resistance is Q sub 2. You set up the same equation for tank 3. So A3 dH3 dt is equal to Q sub 2 minus Q sub 3. So these are the first three starting equations that you will be using. And we'll clear my markings now so we can go down. Okay. After you're done with the 6 working equations, actually you can set up your equations as you go along. You need not have it written like this. That's what I did in mine. So if you're going to evaluate equations 1 to 6 from this one, I have simply translated all the small letters to capital letters because anyhow, all I have to do is evaluate these 3 equations at steady state, and these Q's and this H will have the subscript S, and then I will subtract it from the original and have this one. So I directly change now the Q's and the H to capital Q and capital H. So that's what happened here, and I cross multiplied the linear resistances R1, R2, and R3 on the left side. So your 1, 2, and 3 equations here now became 1 prime, 2 prime, and 3 prime, which you can, after that, perform Laplace transformation. Okay, so capital and then performing Laplace transformation will now make all the variables, deviation variables, as functions of S. So that's for equation 1 prime, 2 prime, and 3 prime. For this one, I also did it just like what I did in here. I changed all the variables to deviation variables. Now on the premise that I know already, and you know already how to change the actual variables to deviation variables. So change it to capital letters and then evaluate it at steady state. So you evaluate its Laplace transform. So when you change it to capital letters, you have to evaluate each of these equations at steady state and subtract it from the original, converting it to capital and then taking Laplace transforms. So you have these equations now coming from 4, 5, and 6. So I have labeled it 4 prime, 5 prime, and 6 prime. If you're going to eliminate Q sub 1 of S, Q sub 2 of S, and A sub 1 of S from equations 1 prime to 5 prime, not including 3 prime, it will give you this particular equation. So this is actually the transfer function of 2 tanks that are said to be interacting, the one that was shown to you yesterday. So you have this one. I used it directly in here, and I computed on this side the taus that I am needing. So you have tau 1 and tau 2. So given values are substituted, and these are the values for tau 1 and tau 2. Substituted in here, so you will have now the transfer function of the first 2 tanks that are interacting as 2 over 4s squared plus 6s plus 1. So this is the first requirement, that you are to write the transfer function of H2 of S over Q of S, by the way. So this is Q of S. I'm miswriting the S here. Your Q should be also a function of S. So I did not show any more class the process of using the equations 1 prime and 4 prime in determining this one. Okay, so I leave that to you as an exercise, but you will use all of these equations to determine the overall transfer function of the system. But since you know this already, so I just made use of it directly. Now we're done with this, with the H2 of S over Q of S, then we can go to H3 of S over Q of S. So I'll share a new document. I hope you can see it. Okay, we have it enlarged. So as for H3 of S over Q of S, you need to set up a new equation between tanks 2 and 3. So you did this one. This is the Laplace transform actually coming from equation 1, 2, 3, 2 prime and 3 prime to 6 prime. Okay, so you transfer the H3 of S in this side so that it will be combined with the H3 of S here. And you have now H3 of S in the left side. Combining this fraction with this will give you this expression. And what is left on the right side is H2 of S over R2. Now you have here an expression which is h3 of s over h2 of s. Now from in here. So if you simplify, you will have this one. Okay? Now it's our rule when we take the Laplace when we take the transfer function, or we determine the transfer function of several tanks in series, that we multiply their transfer function. So what we did here to get h3 of s over q of s is make use of this one, the h3 of s over h2 of s from our material balance on tank 3, and multiplied it to the transfer function of the two tanks in interacting fashion in series, which was shown to you in the first page. So our answer there will multiply by this one. So if you see, we get to cancel the h2 of s. So giving you h3 of s over q of s, which is our goal. So these are the two expressions that you are getting when you multiply these two. So the transfer functions of systems in series are multiplied in the case of non-interacting tanks in series. So we did that in here because we already have this one. We already considered that the first two tanks that were connected in interacting fashion as one system, which is connected to the third tank. So we're allowed to do multiplication. And this is the overall transfer function. So if you simplify, this is it now. Okay? The overall transfer function which we need for letter A, the h3 of s over q of s. So this is needed together with that of the h2 of s over q of s. Now, next thing that we do is substitute the Laplace transform of the forcing function in the first tank, which is that of the unit step function 1 over s in this transfer function, and have it inverted. So your h3 of t, the inverted h3 of s, will actually be the inverse Laplace of this q of s, which is 1 over s times this one. It's like this q of s, you will change to right here. This one has to be changed to 1 over s. Okay, wait lang ha. So it has to be changed to 1 over s, and you do this one, the q of s, and you do cross multiplication. So when you do cross multiplication, this will be like 2 over s, and all of this expression is copied. So you have quantity s plus 0.5 and quantity 4s squared plus 6s plus 1. So you're going to have this inverted. And of course, you know already that you can use method of partial fractions in this case in finding h3 of t. So we'll do that, but we can also use Laplace transforms of integrals, which allows us to only invert these two expressions in here, get the inverse Laplace of these two expressions in here, and the s here entails that you will integrate from 0 to t the corresponding function of t if you have 2 over this thing inverted. So what happened is this 2, I did not consider that anymore. I'll just simply multiply later my answer here by 2. So you'll have this particular expression inverted. And what I did, I converted the quadratic form of the function of s in here into two linear functions. So you can see I have 4s squared plus 6s plus 1. It could be converted to two linear factors, s plus 1.31 and s plus 0.19. If you're going to multiply these two, what you're going to get is this one. Okay, the 4s squared plus 6s plus 9. If this is multiplied. So I use the equivalent linear factors or this. If not, you can still use this, you can still process this using the method of partial fractions. But you have to recall in integral calculus that if you have a quadratic factor, you will have two partial fractions equivalent. One will have the variable in the numerator and the other one will simply be a constant. So in this case, class, ang iasining equivalent partial fractions will be 2. You will have AS over this and B over this, or that's the AS plus B over this quadratic factor. So I hope you can still recall that one from your integral. But nonetheless, this part here is just the mathematics of how to get the inverse Laplace of this. But if you'd rather do the long method of performing for the entire expression, the method of partial fractions, then you may do so. In here, I'm just using the corollary of the Laplace transforms of integral. That way, I will not have to do partial fractions for the entire expression. Okay? Now, this is the part which will let you determine the H3 of t. So, this is on the premise, again, as I've said, that you can still recall this application from advanced engineering mathematics, but I'm sure this was not covered to you. But nonetheless, if you have performed a method of Laplace transform, this will be your corresponding H3 of t. Okay, this is your corresponding H3 of t, where you can substitute t equal to 0 and t equal to infinity. Or, as I have mentioned a while ago, you can use the initial value theorem and the final value theorem. So, okay lang na siya kung ang ginapangayo sa problem is H3 of 0 and H3 of infinity because you can use those theorems. But if it's a specific time, let's say, for example, H3 of 1 or H3 of 3, where in time is 3 minutes or 3 seconds, then you really need this one. You need the inverted form of the H3 of S. That way you can substitute time and find the value of H3 of S. Now, so far, do you have any questions as to the process? So, no questions. So, in this case, let me go back to the problem, what the problem requires. So the problem requires you to find H2 and H3 of S over Q of S. So that's for letter A. And for letter B, you are to determine H3 of 0 and H3 of infinity, and you are to sketch. Okay, so I'm going to show to you the third page of the solution now. We have this new screen. So your H3 of 0 and H3 of infinity would be using the initial and final value theorem. So I've placed the answers in here. It was already discussed in class how you're going to evaluate it. So your initial value theorem evaluates the limit of the product of S and your H of S, the H of S that we have determined a while ago. So in that case, that would be S times H sub 3 of S as S approaches infinity. If you're going to do that, you will have an answer of 0. If you are, in this case, if you're getting an indeterminate form, as discussed in your differential calculus, like infinity times 0 or infinity over infinity or 0 raised to 0, you have to use the techniques that were covered in differential calculus to determine and find the specific value of the function. You can't just simply write infinity times 0 or infinity over infinity, something like that. So you have to use those techniques like L'Hopital's rule, writing it in the form of a rational expression, dividing the numerator and the denominator by the variable having the highest exponent, and so on and so forth. That way you can convert the indeterminate form to something that is specific. And in this case, that is 0. Now, in using the final value theorem, there's no worry, class, because all you have to do is just substitute 0 for all the S in the expression, the corresponding product of S and H3 of S in this case. Okay, and the answer for that is 4. Now, the purpose of, so if you're wondering why get the H3 of T, Why do we need to get the H3 of t and go through the process of the method of partial fractions if we can use the theorems here? Referring to the initial value theorem and the final value theorem, you need the H3 of the expression so you can have it plotted. You could have it plotted in here. So since you could see in here, class, that your final value is 4, meaning the value of H3 of t will be asymptotic to this value, which is 4. The behavior of the curve, specific behavior of the curve, or how it will look like, will depend on your substitution on the H3 of t, the inverted H3 of S. So all you have to do is substitute values there from 1, 2, 3, 4, 5, and so on, and check what will be the shape of the curve. In this case, the shape of the curve would be something like this. Okay, it's like an S. So there is sluggish already. There's a sluggish response of the level of the liquid in tank 3 for a unit step change in the flow rate to tank 1. Okay, so for the answer to letter B, it would be this one and this curve in here. You have any questions? So everything clear? Are you still there? Sige. You only get to see a 1 heart. Sige, harap pa ka mo. So you get it. So we'll go now to the second sample problem, and that's 7.5. Okay, this one is a 3-tank non-interacting, 3 non-interacting tanks in series. Okay, I'll read the problem first. That way you'll know what is that thing that is shown to you. So this is the problem. Okay, so this is 7.5. You're given 3 identical tanks that are operated in series in a non-interacting fashion. For each tank, the R is equal to 1 and the tau is equal to 1. If the deviation in flow rate to the first tank is an impulse, so impulse function of magnitude 2, determine an expression for H of S, where H is the deviation in the level in the third tank. So we can have it represented as H3 of S. Then letter B, you are to sketch the response of H3 of S, or rather of H3 of T, and obtain an expression, of course, for H3 of T. You cannot have the sketch unless you have the expression for H3 of T. Okay, so this is our problem. You may take a screenshot of this if you don't have a copy it there with you. And we'll now go to the solution. Okay, so this is the solution that was shown to you a while ago for that problem 7.5. So I have written the given here. We have 3 tanks. This is the R, this is the tau. They are identical. And your Q, the deviation of the level to tank 1, the deviation rather of the flow rate to tank 1, not level, is 2, and it's an impulse function. So you see, it's just simply written as 2 because the impulse forcing function has a Laplace transform of 1. A unit impulse function has a Laplace transform of 1. It's the only Laplace transform which doesn't contain the S. So since in here the magnitude is 2, so we just simply write the Q as 2. So no S for that. So these are your required information. So H of S, HT of T, and versus t. So you need to sketch it, and you have the h of t, all referring to tank 3 because we're asked to determine the response of this system. So that would be referring to the level of the last tank in series. So from the derived transfer function of the two non-interacting tanks in series, ye have now this one. H2 of S over Q of S, this was shown to you also yesterday, equal to the linear resistance to tank 2 divided by this 2. So they are similar, so you will have something like tau S plus 1 squared in this case because your taus are the same. They have the same R and tau. So this is just for the first two tanks. So for the third tank, I place again here the derivation, and you will have this expression for the relationship between volumetric flow rate through the linear resistances for tank 2 and tank 3 in relation to the levels in those tanks. So you have this. You have here the material balance, the variables in deviation form, and its Laplace transform. I think you know this already. The purpose of this is you will replace the Q2 and the Q3 in here in terms of levels. Why express Q2 and Q3 here in terms of levels? Because your unknown function here is in terms of level. Okay, so these are your equations. If you substituting 2 prime and 2 double prime to 2, as I have mentioned just a few seconds ago, so this will be the expression. You get rid of the Q's and you change it in terms of H, or that's the level. You have it in here, then you have an expression relating level of tank 3 to level of tank 2. So you have combined this one you transferred in here first, then you have this and you have it combined, and you will have this expression. So all algebra. And you have this expression relating level of tank 3 to level of tank 2. Now, why get this? Why get this? Because you need it together with this one to get the overall transfer function of the entire system. This one is just for the first two tanks. So if you want the third tank connected to the first two, as principal, you need to multiply its transfer function to the transfer function of the first two. Okay, so we'll go to the next page in the solution. Share. So you'll have here, make it even bigger. Your H3 of S over Q of S will be H3 of S over H2 of S times H2 of S over Q of S. So just multiply the two transfer functions, and this will be the corresponding overall transfer function of your system. H3 of S over Q of S is this one. The systems are identical, so you have a simple 1 over S plus 1 raised to 3. So if your Q is an impulse function of magnitude 2, so you replace the Q of S here with 2. So you have a 2 in there. Inverting this is very easy. You know how to invert this one, just the expression. So this is using the shifting of the function of t. So if this is inverted, you have t squared e raised to minus t as its inverse Laplace. You will know you're correct if you're going to take the Laplace transform of this, and you'll go back to this expression. Now you need this one because you need to, shall I say, sketch as the problem requires it. You need to sketch the response. So this response is having its highest value at 0.54, and then it will die down. Okay. So it is something like that, and then goes down. It will be prolonged in here depending on the time. So if time reaches infinity, of course your h of t will be infinity. So asymptotic sila. Sorry. this would be a case of, sorry, not infinity class, I stand corrected. If you will substitute e raised to negative infinity here, that would be 0. However, this one will be infinity. So you have infinity times 0. That's an indeterminate form. So you have to recall what you have learned in your differential calculus on how you will get the specific value of h of infinity. That way you will know the behavior here as t approaches infinity. My guess it would be asymptotic to h of t equal to 0. But it has to be shown in the solution why it is 0. So you have to recall what you have learned in your differential calculus and how you will evaluate this expression, which is actually by direct substitution is infinity times 0. So you should have it converted. Okay, that's it. So this is the plot of the said response. So anyway, it's just asking for the response and the plot. Okay, let me check. So you are to write the expression for H3 of S, sketch the response of H3 of T, and obtain its expression. So we have done that as already. Okay. Now, next thing we do is we go to problem 7.6. So I will share new screen now. So this time we'll be talking of a different system, and that's a mixing system. For our last sample problem. So in the two-tank mixing process shown in the figure, X varies from 0 pounds salt per cubic feet to 1 pound of salt per cubic feet according to a step function. So meaning the original concentration X, which is 0, was changed to 1 pounds per cubic feet according to a step forcing function. So it's a unit step forcing function because the change is just 1. At what time does the salt concentration in tank 2 in here reach 0.6 pounds of salt per cubic feet? Now the hold up volume, or simply the volume of each of these tanks, is 6 cubic feet. Okay, so we have just one required information, and that is the salt concentration. That's Y2 for tank 2. How long will it reach 0.6 pounds of salt per cubic feet? So it's the time. It's not the concentration because the concentration is already given. So what time will it reach that particular concentration? In this case, of course, you need to get the transfer function of the entire system. Okay, get the transfer function of the entire system. If you're going to look into its solution, okay, I'll share a new screen now. So this is our system. We have two mixing tanks. And this is the volumetric flow rate. Tank 1, X is the concentration in the inlet of tank 1. And the concentrations here in tank 1 and tank 2 are represented here as C sub 1 and C respectively. Or you can use also in this case, you can also use in terms of the mixing tank, this could be represented as Y1 and this could be represented as Y2 because we have X and Y for a mixing system. But in my case here, I represented it as C because I want to be reminded that I'm actually getting concentrate. I'm working on concentrations. Now, if it's just X and Y in my case, they are just ordinary variables. But nonetheless, if you want to represent it as X and Y, it's okay. So your X changes from 0 to 1 according to a step function. Okay. So 1 pound of salt per cubic feet. So you are required for that time in which, in this particular case, in my representation, Y2 is equal to 0.6 pounds of salt per cubic feet. Right? So you will do material balance in this case for each of your tanks. So if you do material balance, it would be something like this. So material balance in tank 1, the volume of each of these tanks are the same. So I just presented it as V because they're the same. They're equal. So volume times the rate of change of the concentration in tank 1 will give you a set unit for this term, which is in mass per unit time. Okay? Because your concentration is in mass per unit volume. So you will have it as the volumetric flow rate into the tank, which is 3 times its concentration, which is X. Okay? It's represented here as X. And you subtract the same volumetric flow rate 3 and its product with C sub 1, the concentration at any time in tank 1. So this is your input. Your input in this case is QX. Your output actually is also QY. Y here was changed to C1 or C sub 1. Now, in deviation form, you can change that in deviation right away because you will just evaluate this at steady state. This will not be changing at steady state, so this is 0. The evaluated equation at steady state subtracted from this will give you the equation, the original equation in deviation form. So, diretso ko na lang siya ginsulat. And then, I took Laplace transforms. I substituted the value 6 to the V. And I have this for C sub 1 of S divided by X of S. So this is your output. This is your input. So it's 3 over 6S plus 3. If we rewrite the expression in such a way that you will have tau S plus 1 in the denominator to know the gain for the first mixing tank, you will have it in here. So your tau is 2 and the gain is dimensionless. It's 1. Now you do the same for tank 2. So you have V, dC, dt. This one is C1, concentration in tank 1. Concentration in tank 2 was presented as C. And you have 3C1 minus 3C in deviation form, in Laplace transform, and then you have this Laplace transfer function for the second tank. This is the transfer function of the first tank, and this is the transfer function of the second tank. Okay, we don't have a liquid level system here, but we have a mixing system. So what will you do to get the overall transfer function of these two tanks? Of course, you will multiply. The goal is you will have C of S over X of S. So how will you attain or how will you obtain C of S over X of S? Okay, if you will simply manipulate, then there's a need for you to multiply these two. And that will be shown in the next page. So in the next page, this is the next page with the solution. Your C of S over X of S is equal to C of S over C sub 1 times C sub 1 of S over X of S. Transfer function of the first mixing tank, transfer function of the second mixing tank. So you have this one, so you have this as the overall transfer function. If X of S is equal to 1 over S, there's a step change in the concentration of the feed because it started with 0 to 1 pound of salt per cubic feet. So your X of S is 1 over S. So your C of S, if you substitute 1 over S here, will be 1 over S times the quantity 2S plus 1 squared. Again, I made use of, in this case, you need to use method of partial fractions. Okay? So you need to get the inverse Laplace of this expression. Your C of t in this case is this one. So the process of inversion, the detailed inversion is not shown anymore. So this is your C of t. So how long will it take for this C to reach 0.6? So you have 0.6 is equal to 1 minus this. So you have this as your final equation. And you cannot explicitly solve t in this case. So it's a trial and error thing. So if you're going to do trial and error at time reaching 4 minutes, more or less 4 minutes, the value of the C in tank 2 will be 0.6. Now, in case you're wondering why this C actually class, right here. So the C that you have is actually deviation form na siya. So it's actually the small c minus the C at steady state. Okay? That since the initial concentration of the feed to tank 1 is 0, that would also be the initial concentration of all the thing inside the tank, because then at time equal to 0 at steady state, we can deduce that your tank does not contain any salt. There's no salt that is being fed to any of your tanks, specifically your tank 1. So this one class will be 0. The C sub S will be 0. So it's automatic that the deviation is equal to the current concentration because you started with nothing. So the concentration for each of your tanks is 0 for the salt. So this is the answer. So it would take 4 minutes for the concentration in tank 2 to reach 0.8. Okay? Any question here? Okay, I still have around 10 minutes, so I'll use the last 10 minutes for the last problem. Okay, class, I'll share again Kauhan. I'll discuss this one because again, in this one, you have to write your material balance for the first tank because it's different than the ones that we have already derived. Okay, share ko again. So this is 7.7. Starting from first principles, derive the transfer function H1 of S over Q of S and H2 of S over Q of S for the liquid level shown. The resistances are linear, so both are equal to 1. And you are to note that two streams are flowing from tank 1, one of which flows into tank 2. You are expected to give numerical values of the parameter in the transfer functions and to show clearly how you derive the transfer function. So the pre-derived transfer function will not work anymore in this case because your tank 1 has two discharges. So two linear resistances where the flow is being discharged. And one goes to tank 2, the other one into the atmosphere. Okay, so you need to set up a material balance equation for this. Although this one will have a material balance comparable to that of a liquid level system, a single tank or a single liquid level system. Okay, now I'll share the solution to this here. So this is our representation. I represented volumetric flow rate through linear resistance RA of tank 1 as Q sub A. This is Q sub 1 for linear resistance R1. You have here the areas of the two tanks. This is two tanks connected in non-interacting fashion. So non-interacting gyapon sila. Only that this one has two outflows or outlet flows. Now I'll go to the next page, the last page in here. So this is purely, again, mathematics and material balance for each of the tanks. If you do material balance on tank 1, I hope you can see it already. So you will have these two volumetric outflows. They should be represented properly in terms of levels. So Q sub A is H1 over RA, or that's H1 over 2. And Q sub 1 is H1 over R1, and R1 is equal to 1, so it's H1. You substitute here, it would be like that. If you combine these two, that would be 3 over 2H1. At steady state, this would be 0, and you will have S here as subscripts for Q and H. Subtracting this from the original gives you this one. You can write it in terms of division variables now. Changing small h sub 1 to capital H sub 1 because of this. And the two division expressions of the two variables were changed to capital letters. Once they are already in division form, you take the Laplace and write your transfer function in terms of output over input. Your output is the level in tank 1 divided by changes in the input. So you have this one. So you will have, you have here 2s plus 3 halves. If you're going to combine this, you will have 4s plus 3 divided by 2. The 2 goes up here in the numerator. So this is your transfer function for the first tank. You do material balance on the second tank. It's just like any ordinary liquid level system. Inlet flow rate is Q sub 1, outlet is Q sub 2. You can write it in division form right away. Take Laplace. Relationships of volumetric flow rates through the linear resistances are this. Go back here and substitute, change this Q1 and Q2 in terms of H. So you have this one now. And then since this is H2 and this is H2, combine this into one expression and get Laplace transform in terms of output over input. So you have H2 of S over H1 of S as this. Simplifying, substituting the R values, you will have this. Again, how to get the overall Laplace transfer of the system. That would be Laplace transform of the first tank to Laplace transform. Transfer function of the entire system will be transfer function of first tank to transfer function of the second tank. And you substitute. And this will be the corresponding expression. So anyway, the problem is just asking for the transfer function of the system and that of the first tank. So this is it. H1 of S over Q of S and H2 of S over Q of S. As to responses, all you have to do to specific types of input is appropriately or correctly place here the Q of S expression for the kind of disturbance that is happening to your input. And you just need to invert the corresponding H of S expression, whatever that is, to get the H of T and determine its value for the specific time in which the problem requires you to determine its value. Okay? So far, any questions to what we have discussed? I'll stop sharing now.